So in our previous class, we have already seen how to find or how to apply the Gauss theorem in order to find or determine the electric field due to various charged objects. We have seen the electric field due to a long wire, and then we have also seen how to find electric field due to a thin plate, thin charged plate of infinite length of or infinite spread, right? So this we have discussed. And what happens if the plate is thick? Even that we have discussed. Then we saw what if the plates are kept, what if two plates are kept parallel to each other, two charge plates kept parallel to each other, what if the charges are same, what if the charges are different, right? So, and what will be the electric field on the two sides, outer sides of the plates and in between the plates. So these are few things which we have already discussed. Now the next application or the next scenario in which we have to find the electric field is due to a uniform charged thin spherical shell, right? So basically due to spherical shell. So shell is what? Shell is, as you can see, it's spherical shell. So sphere, and if it is hollow inside, that is called a shell, right? So that is the difference between a shell and sphere. Okay. Deleted or not? Yes, it is deleted, but there will be numericals on this, so there is no point in leaving this topic, right? And it's not that that it is very difficult, so that's why we are doing it. It's very easy. Okay, and whatever portions are deleted from your board exams, right? uh, there are some topics which are deleted, and it makes sense that you also don't go through those topics because they are deleted completely. But there are most of the topics which are deleted are not deleted completely. So there will be some application or some numerical or some other theoretical portions. So every concept in or every topic in physics will have concept and theory, will have numericals, and you can say some logical questions based on this. So in sometimes application will be removed, applications are removed, sometimes only concept is removed, application is there. So that's why we are doing this topic as well. Okay, so let's start again. Spherical shell, you understood shell is different from a solid sphere. Solid sphere has a bulk inside, while a spherical shell will have no bulk inside, that is, it will remain hollow from inside. So that is a spherical shell. Okay, now if you have a shell which is spherical in shape, right? Let's say the center of this shell is at this point, let's say that is O. Then you may have to find, or you will again have different regions here where you can find the electric field. You may have to find electric field here at this point, where when this point lies outside the plane. Then you may have to find electric field at a point which is on the plane, or that is on the surface. And sometimes the other or the third region is this, that is a point which is inside the plane, inside the shell. So this is point in, this is out, and this is on the surface. So we will go through this one by one. So let's try to find out the field outside the shell. Let's try and do that. That is at a point P outside the shell. So if there is a point P which is outside the shell, let's say that this is that point. So as we have seen earlier also, the procedure is fixed. What you have to do is you have to come up with a Gaussian surface right? And you choose that surface in such a way that the electric field at any point is constant and has the same direction with respect to the area vector. So if you take the spherical, the imaginary spherical surface again here, which will be concentric with the center of the sphere, the given sphere. So it will be that, it will be a Gaussian surface. Why? Because if you take any surface here, let's say very small surface here, which is ds, then this ds, then this ds and de both will be in the same direction. That is, theta will be equals to 0 degree. You take it at any point on the surface, you will see, you will get the same thing, right? And at any point, what will be E? E will be equal to what? It will be equal to whatever charge is placed here at the center, right? That into k divided by r square. So electric field is also going to be constant. So that's why we are taking this, not d, we are taking this Gaussian surface. So Gaussian surface is finalized. Now from the Gauss law, you just have to apply the Gauss law. So this phi e, that is flux, will be equal to the surface integral of E dot ds, right? And we know that this is equals to q divided by epsilon naught. Now what's next? This is the application in which we have to find the electric field, right? So we'll do that. Now EDS, we know that it is equal to q by epsilon naught, and we know that the angle between E and ds is always 0 degree. So E dot ds is nothing but EDS cos theta. So that will be equal to EDS. So this is E ds, the integration of EDS, and that is equals to q divided by epsilon naught. Now in this, if E is constant, you can take it outside, and it is only the surface area, right? The total surface area. And what is total surface area? It is pi r square. So that means E into 4 pi r square is equals to q divided by epsilon naught. And from this you can say that E will be equal to q divided by 4 pi r square into epsilon, or 1 by 4 pi epsilon naught into q divided by r square. Now if you observe this final expression, it is same as the expression for electric field due to a point charge at a distance r from the center. What is r? This distance is r. The radius of the outer sphere is r. The radius of inner sphere is capital R. Right? Okay. Now next, if you see, this charge was actually distributed over this surface, right? So let's say the distribution density, charge density of this is sigma. Uniform density, let's say that is sigma. That means the total charge is actually sigma into, sigma is what? Sigma is charge per unit area. So sigma into 4 pi r square is q. So this q can be, yeah, q can be replaced with sigma into 4 pi r square. And if you do that, what is E here now? E is 1 by 4 pi epsilon naught into q, which is sigma into 4 pi r square divided by r square. So this 4 pi r square and 4 pi gone. So this is again sigma divided by epsilon naught, which is similar to the Okay, there is one catch here. This is not 4 pi small r square. This is 4 pi capital R square, right? So here it won't cancel. So R square is still there, but 4 pi is gone, right? So this is sigma by epsilon naught into R square divided by R square, right? So there are two expressions for electric field in this case, right? If you notice, E is equals to 1 by 4 pi epsilon naught into Q divided by R square, and the other expression is derived from this expression itself by substituting Q is equals to sigma into 4 pi capital R square. So that's if you do that, it will be Q divided by epsilon naught into R square divided by R square. So these are the final expressions in this case. That is when it is outside. The point is outside where you are finding the electric field. So electric field due to a uniformly charged thin spherical shell at a point outside the shell is such as if the whole charge were concentrated at the center of the shell. It that's what the expression for electric field due to a point charge is, and the same expression you got here as well. So that's why we say that it behaves or it is similar to that. Okay, now what will happen if the point, if the point where you are finding the electric field is on the surface? So let's do that. P is on the surface of the shell. So nothing changes here actually. You have to follow the same procedure, and in that case electric flux will be still equal to E dot ds surface integral, and we have to equate it to Q by epsilon naught, right? And we know what is Q and we know what is EDS by now. So EDS integration will be equals to Q by epsilon naught, and E now only difference will be that ds integration is 4 pi capital R square, and that is equals to Q in Q divided by epsilon naught. And what is Q? You can substitute that as well. We'll do that later. So E is equals to 1 by 4 pi epsilon naught into Q divided by R square. That is 1. And now, as you know, Q is equals to sigma into 4 pi R square. If you substitute that, you will get E is equals to Q divided by epsilon naught. So it's just a special case of whatever expression we have seen earlier. In that, we just have to substitute small r to, or we have to replace the small r with capital R. That's all, right? So here E is equals to Q by epsilon naught. That means now if you see or we'll do the comparison later. So that is about that is the electric field at a point which is on the surface of the shell. So electric field due to a uniformly charged thin spherical shell at a point on the surface of the shell is maximum. We will see that. Coming to the last one. Last one is at a point which is inside the surface. So a point inside the surface means what? Go ahead with the same procedure. There will be a small radius, a radius r, which is smaller than capital R, right? Otherwise, there won't be any difference. I hope you understood what I'm saying. This is the sphere and your Gaussian surface, because the point is here. So you have to find the Gaussian surface, or you have to take a Gaussian surface passing through that point P. So that will be nothing but this sphere, which is inside this. So the actual radius is sorry, the actual radius of the sphere is capital R, and this is R. That is the only difference, right? But all the charges are on the surface. That means there is no charge inside the surface, but in the interior of this shell there is no charge. So that means Q is 0. So whatever this EDS will give you, E into S, which we know that it will be equals to 4 pi R square, that will be equals to 0 by epsilon naught, which is equals to 0. That means this E is also equals to 0. So now if you see, there are three cases. That is, first, when it is out. So in this third case, you have got E equals to 0. Remember that. When it is outside, E was equal to the two ways of doing this, that is 1 by 4 pi epsilon naught q divided by r square. And when it is on the surface, we saw that E is equals to 1 by 4 pi epsilon naught q divided by capital R square. And when it is in the surface, or sorry, inside the surface, we know that electric field is equals to 0, right? So now if you see this here, this R is less than capital R. So that means what? As you are coming towards the sphere, right, the distance R will be decreasing, and this will be the value where it will be equal to the radius of the sphere, the actual spherical shell. So in this case, obviously, this electric field which you are finding here, this is the maximum value of electric field which you will get. And before this, it is 0. So if you have to plot, if you have to understand this, right, you can do it like this. Say from 0 to R, let's say this is 0 to distance R, right? What is the electric field? It is 0. So the electric field here is 0. That is inside the sphere. As soon as it becomes R, the electric field reaches the maximum value, that is Emax. What is Emax? This is Emax. 1 by 4 pi epsilon naught q divided by R square, or q by epsilon naught. So this is the maximum value which you will get when the distance is R. And after that, what happens? After that, this value keeps on decreasing because it is inversely proportional to R square. This is how the electric field due to a thin spherical shell varies with distance from the center, right? And this fact that electric field inside the shell is equals to 0, this will be used for electrostatic shielding. We will learn that in detail later, right? But for the time being, you should know that inside any cavity, cavity means shell. It's not only a spherical shell, it can be of any type. But inside the shell, inside the cavity, the charge, total charge is 0, and it is due to this fact that the electric field is also 0. And that means there won't be any electric field inside the shield, inside the shell or hollow cavity. So that's why that is an important point actually. Okay, so that is about the application of Gauss theorem. That is all about the application of Gauss theorem. Next topic is capacitors, so we'll continue with that now.